So hello and welcome back to my channel. This is the second part of a video in which I solve a problem from Griffiths Electrodynamics textbook, a problem from the very first chapter, which is the chapter which explains the calculus of vectors in a lot of detail, and is a very interesting chapter. So in this problem we are given a particular vector field, and using that vector field we have to verify the divergence theorem. We are also given a particular closed surface, which is the surface of an ice cream cone. So the divergence theorem relates two types of integrals. One integral is a volume integral, an integral of the divergence of that vector field calculated over the entire volume of the ice cream cone, and the right hand side integral is a surface integral which is calculated over the entire surface of the ice cream cone. So in the first part of the video we saw in a lot of detail, we try to understand from a very close perspective how the spherical coordinate system works, because we are given the vector field in a spherical coordinates r, theta and phi. So we had reached this point where we had understood how to write the elemental volume in spherical coordinates, how that elemental volume is achieved by moving very small distances progressively in the r, theta and phi. No, not progressively, it's like those three operations are independent, because those three directions are perpendicular, and also because the distances that you're moving are extremely small, and so they are independent of each other, those three directions. It doesn't matter in which order you make which order you move the small distances, whether you move in the r direction first or whether you move in the phi direction first. So basically, in general, when we are moving in the r direction, so small distance in the r direction, that small distance is dr, and when we move in the theta cap direction, and theta, we also saw in a lot of detail the meaning of these r cap, theta cap and phi cap directions and how to understand them. For example, the theta cap direction is the direction in which, if you move in that direction, only theta varies and r and phi remain constant. And so you should definitely watch the first video again if you have watched it also, and because it will be a nice recap, because there were a lot of details involved, a lot of deep discussion involved in that video. So now we are going to start from this point where we already have the elemental volume and we are ready to calculate the volume integral. We had already achieved the value of the divergence in the first part, and this is the divergence, 4r cos square theta by sine theta. This is the divergence of a vector field is a scalar field. It's just one quantity which depends on r, theta and phi. In this case it's independent of phi. So this is the divergence of V, and this is the elemental volume that I multiplied it with. So I get this triple integral. Now we also need to understand how to interpret these triple integrals. What is the meaning of this triple integral? So essentially what we are doing is we are integrating. What is the meaning of an integral? An integral is just a sum of an infinite number of quantities, and all those quantities are infinitely small. So it's just a sum. It's just a special kind of sum in which the number of elements is infinitely large, and usually the size of each of those quantities is infinitely small, so that the total sum comes out to be something finite. So if it's a sum, I have to go to every point inside the cone, because it has to cover the entire volume of the cone. I have to go to every point inside the cone, and close to that point I will have an elemental volume whose magnitude will be r square sine theta dr d theta d phi, and depending on where I am right now, what is the value of r right now, what is the value of theta and phi right now, those are the coordinates of the point at which I am currently at. Depending on those quantities, I will have a particular value of this elemental volume, and I will multiply that elemental volume with this divergence, which also depends on r, theta and phi, and I will get a particular quantity. So attached to that particular point inside the cone, I will get a particular quantity. So suppose r is equal to capital R by 2, theta is equal to, let's say, pi by 10. I'm just taking random values here. Phi is equal to, let's say, 0. So attached to that particular point with those particular coordinates, I will get a particular value of this entire product on the right hand side. And the meaning of this integral is that I have to include all those points inside the cone and add this quantity for each point, calculate that quantity for each point, and multiply it by dr, d theta, d phi as well, which are the small changes in r, theta and phi, and add all those terms, and that will give me the entire integral, right? So turns out that I can do this operation for one variable at a time. I can separate them out, because here this total thing that I'm getting, the r, the part which depends on r, the part which depends on theta, and the part which depends on phi can be separated out like a product here. So this integral becomes a product of three separate integrals, right? So what I can do is basically I can sort of use a distributive kind of logic. So I can separate these two parts, these two integrals, the cos square theta integral and this d phi integral. I can put a bracket over here, right? And I can say, and then within this bracket I can bracket this part also. So I can say that keeping r and theta constant for the time being, I will add up all the terms over all the value. I will add the terms over all the values of phi, right? So it's like you can first understand this in the context of a two-dimensional surface, like the xy plane. So suppose I am, you can draw the figures yourself. You can I will explain in words, but you can draw the figures yourself. That will help your understanding better compared to if I had given you the figure right in front of you. So you can draw a square on the xy plane. The square, the vertices are 0, 0, 0, 1, 1, 0 and 1, 1. So it's a unit square on the xy plane. Now if I want to say that I want to integrate, I want to calculate a double integral, which is the integral of dx dy over this entire square surface, and I want to include only the square surface and nothing else. So what will I do? So I have an integral dx multiplied by dy, and I have to integrate this. I have to find this value dx dy for each point and integrate it. In fact, you can say that the dx dy is multiplied by 1. So, or you can multiply it by some function of x and y. Let's say we want to integrate xy square dx dy, and I want to integrate this over the entire square of size 1 in the xy plane. So I can understand it in this way, that if I integrate first over all the values of x and take y constant for the time being, suppose I take y is equal to 0.5 for the time being, and I integrate over all the values of x, then it doesn't matter. I can do that. That is a valid way of doing that, and the reason for that is comes from the limits of the integral, and that is what I'll explain right over here. That if I want to cover the entire volume of the ice cream cone, for example, what do I have to do? So let us look at the span of the cone. So suppose I keep two of my quantities constant. Suppose I keep R is equal to capital R, and I keep phi is equal to, let's say, the phi which is given over here in the figure. Let's say phi is equal to 300 degrees. So I'm at this point, right? And R is equal to capital R. So yeah. So I am at this circle, which is the rim of the ice cream cone, has the value of R is equal to capital R, right? So I'm at this point, right? And now I start varying theta between 0 and pi by 6. So I will trace out this curve, right? I will trace out this circular arc, right? So on this circular arc, R remains constant, phi remains constant, but theta varies between 0 and pi by 6, right? So if I just vary one of my variables, theta, I trace out a curve in three-dimensional space. Instead of theta, if I had varied phi, for example, kept the R constant, kept theta constant, let's say theta is equal to pi by 6, R is equal to R, and phi is equal to 300. I'm at this point, but now I start varying phi to all values between 0 and 2 pi. So I trace out this entire circle. So this should be quite intuitive, right? That if I vary only one of the quantities out of the three, I will trace out a curve. And similarly, if I vary only R, I'll get this line. So now if I start varying two of the quantities at the same time, I will trace out a surface. That makes sense. And if I vary all three of them together, then it will give me some kind of volume, right? But the important part over here is that the limits in this situation are not interdependent, and you will understand that if you have calculated more triple integral. So this is a triple integral that we're dealing with. You can say a three-dimensional integral with integral involving three variables, right? Integrated thrice over each variable, integrated once over each variable, so integrated thrice in total. The limits could have been interdependent, like the limit of R depends on theta, right? And how will that take place in a real situation? So here I have an ice cream cone, so which has a top surface which is part of the sphere of radius R centered at the origin, right? So the ice cream cone that we are given in the problem has a spherical top surface, and that spherical top surface is a sphere centered, is part of the sphere centered at the origin of radius capital R, right? So instead of that, if I had a cone with a flat top surface, right, and now you had to define the boundaries, the limits themselves are the boundaries, define the boundaries of the cone. So for a particular value of theta, let's say for theta equal to pi by 6, you go from 0 to capital R. But if you decrease theta, so if I am at some other theta, let's say I am at theta equal to 0, for example, then I don't go to capital R, because if I go to capital R, then I go out of the cone, right? So the limit the limits between which small r can vary now, if I have a flat top cone, which I don't have in the original problem, by the way, but if I had a flat top cone instead of an ice cream cone, the nature of that cone would dictate that to integrate over the entire volume of that flat top cone, R cannot vary between 0 and capital R for all values of theta and phi, right? So for particular values of theta, R, let's say for theta equal to pi by 6, R can go from 0 to capital R, but for theta is equal to, let's say, 0, R can only go up to capital R times cos pi by 6, right, which is the distance of this point, from the origin. So in that case, the limits of the integrals would be interdependent, and in a sense you cannot perform the integrals in any order. In that case, in that case you would have to perform the integrals in a particular order. We would talk more about this in a future video about integrals, double and triple integrals, in which case I would make it crystal clear. I know it is the explanation is not as deep as it can be, but sometimes it's better to leave something to the viewer as well, so that they can use their imagination, and because they use their imagination, their understanding becomes better, because they've invested their time and mind to it. So essentially using these limits, so let's again look at how these limits define the entire cone. So suppose I apply only this part first. I only apply the phi part. So I'm at any particular point. Let's say I'm at theta equal to pi by 6, and I'm at capital R. I'm at r equal to capital R. So I'm at this point, and I apply the phi part. So I cover all these points. Now all these points are covered, but this is still just a line, just a circle. Now if I say now I apply the limits r equal to capital R, so then I get the entire conical surface, but I have only gotten the surface. Now if I apply the theta part for each particular value of theta, so if I fix a particular value of theta and vary r and phi, I will get a particular cone. So this is the cone for theta is equal to pi by 6. If I take theta equal to, let's say, pi by 12, I'll get another sharper cone inside, right? But the top periphery, the circular periphery of that cone will lie on that spherical top of the ice cream cone. And so if I take all the values of theta as well, I would have taken all those cones. I would have taken a collection of cones, a family of cones, and taking all of the members of that family together would constitute taking the entire volume of the ice cream cone. So this is how the limits define the cone, and we put the limits and we just perform the three integrals separately, because and we can perform them in any order because the limits are just independent of each other, and we get this answer, which is probably not very difficult for any of you. So this is the left integral which we have finally achieved. So now let's move to the right hand side integral, and for that we have to understand the elemental surface area. And here the surface of the cone can be divided into two meaningful parts. One part is the conical part, and the other is the spherical top. On the cone, again, now I just talked about this, that if I keep one of the variables constant in three-dimensional space, whether it's x, y, z, or whether it's r, theta, phi, if I keep one of the variables constant and I vary the other two, in general I get a surface. So here also, to get the conical surface, it is quite intuitive that if I keep theta equal to pi by 6 and I keep varying r and phi, I can take all values of phi between 0 and 2 pi, and for small r I can take values between 0 and capital R. I'll get the entire conical surface. So a general point on the surface of this cone would be r comma pi by 6 comma phi, because theta is fixed. And again, so defining getting the value of the elemental surface area is extremely easy here, because we know that moving on this surface we can only vary phi. So as long as we only vary r and phi and don't touch theta, we can be extremely sure, we can be completely sure that we are moving entirely on the surface. We are not leaving the surface. As soon as I change theta, so this is all these statements, you should think about them and should verify them, because that will improve your intuitive understanding of the coordinate system, that as soon as, if I'm on this cone, theta must be pi by 6. As soon as I change theta, I have left the surface of this cone. But if I keep theta the same and change r and phi as much as I want to, I will remain on this cone as long as I don't change r beyond capital R, right? So to get the elemental surface area, to get the infinitely small patch of area on this surface, all I have to do is move a small distance in the r direction and move a small distance in the phi direction, because as soon as I've done that, I get a two-dimensional surface, because I've moved in r and I've moved in phi. So if I move in small distance in r, that small distance is dr, and if I move a small distance in phi, I move, that distance is r sine theta d phi, where theta will be pi by 6, because I am on the surface which is defined by theta equal to pi by 6. So multiplying that, so it will be a square, it will be a rectangle, basically an infinitely small rectangular patch on the surface of the cone, and its dimensions are dr and r sine theta d phi. And one more thing which is different from the elemental volume is that this surface area must also have a direction, because it's a vector area. And the direction of the vector area is along the normal to the surface. So if I'm at this point and I've taken a small area, what is the direction which is normal to the surface? The direction which is normal to the surface is theta cap. It is quite intuitive that theta cap, because again theta cap is exactly that direction in which if you move, then r and phi don't change, but only theta changes. And so it's like changing in the r and phi directions is like remaining on the surface, because theta is fixed on that surface, but making a change in the theta direction is like leaving the surface. So theta cap is the direction which is perpendicular to the surface, because as soon as you move in the theta cap direction, you have left the surface, right? And also geometrically you can understand that from this particular figure, so if I move along this curve, I am changing theta, and this curve is the circle. So is the circle centered at the origin, and this is the radius joining this point to the origin, and so the two of them are perpendicular, and the direction in which theta changes, theta cap, is perpendicular to the position vector. So a small surface, a small vector area on the surface, on this conical surface, is the magnitude is this, and the direction is theta cap. And I've taken theta cap, not minus theta cap, because in the divergence theorem, the elemental surface area, the vector area's direction, the direction of that vector area has to be pointing outwards. Now the same discussion for the top, for the spherical top, and the discussion is the same, that now to define this spherical surface I have kept r constant. So now small r is capital R, but theta and phi can change. Theta can only change between 0 and pi by 6, but phi can change between 0 and 2 pi. And so again, if to get a small patch, I need to move very small distances in the theta direction and in the phi direction, because I can't move in the r direction. As soon as I move in the r direction, I have left that surface. I'm no longer on that surface. That surface has r fixed. So small distance in the theta, again the same discussion, that small distance in the theta direction is r d theta, small direction change in the small distance in the phi direction is r sin theta d phi. So the product of the two gives me that area of the infinitely small rectangular patch on the spherical surface, and the direction would be r cap. So you can try to understand this on your own, that if I am at this at a point on this top spherical surface, if I'm at this point and I want to say which direction from this point is perpendicular to the surface at this point. So obviously the sphere, if the surface is not a plane, the surface is not a plane, so the perpendicular direction to the surface will be different at each point of the surface, because it's not a plane, it's a spherical surface. But if you are at any point here, the direction in which you have to move so that you're moving perpendicular to the surface at that point is r cap. And it's very similar to the previous situation, that because this surface is defined by r is equal to constant, moving in a direction which changes r is essentially moving perpendicular to the surface. So this is just an intuitive way of remembering, of checking, of verifying your answer. So the small area element on this spherical surface is this, and r is capital R now. So we have the elemental area that we needed to calculate the right hand side of the integral, the right hand side integral of the divergence theorem. And this right hand side is, you can also say it's the integral which calculates the flux. So this v dot dA integrated over the entire surface is the total flux of this vector field through the surface, right? So to cover the entire surface, we have to include the entire conical surface and also the entire spherical surface. We are separating this integral into two parts because it's easier to calculate the two integrals separately rather than at once. It's almost impossible to think about how do you calculate the surface integral of the conical surface and the spherical surface at one go. It is very I have not even thought about it, but this is extremely intuitive that we treat them separately, because they are different surfaces which can be if I deal with one of them at one time, they become extremely easy to deal with. So first, calculating the integral over the conical part, we already have v, we are given v, which is a vector field, and we have also achieved the area element which was in the theta cap direction. So when I take the dot product, it's a dot product, v dot dA. So only the theta cap part of v matters because the area element points in the theta cap direction. So this is the integral. So again, I separate out the r and theta part and the phi part. I have already put theta is equal to pi by 6 because we are on the conical surface where theta is pi by 6. It's fixed, so it's just a constant. So theta is equal to pi by 6. I've replaced that, and this is the integral we get. And now, how do you think about the limits? Again, is quite intuitive. To cover the entire conical surface, going back to cover this entire conical surface, you have to vary r from 0 to capital R, so that you reach all those distances, and you have to vary phi between 0 and 2 pi. So you can think about it in the other way, that for example, my r is fixed currently at some value, let's say 3r by 4. My small r is fixed, and I vary my phi. Theta is obviously fixed because I remain on the surface, because I'm only talking about the conical surface. So theta is fixed, that is already fixed, but r is also fixed now, and I vary my phi, so I get this circle. Now for a particular r, if I vary phi, I get a circle. And now if I, with that variation of phi, I superimpose the variation in R from 0 to capital R, I get a collection of circles. Because when R is fixed and phi is changed, I get a single circle. But when R is also varied after that, I get a collection of circles, and collection of circles together span the entire conical surface. So that is like that is how you generate surfaces in 3 dimensions or in 2 dimensions, that you have to vary 2 quantities. To generate a straight line, for example, you only have to vary 1 quantity, but to generate a surface, you vary 2 quantities, and the variation of both quantities superimposed. You know what I mean by superimposition is that if this small r varies between 0 and capital R, and phi varies between 0 and 2 pi, then for any value of r between 0 and r, I take all values of phi between 0 and 2 pi, and for any value of phi between 0 and 2 pi, I take all values of capital R. So you can check that. So it's like a it's like a 2-dimensional array of values. You can say that I write all the even though they vary continuously. I'm trying to give an analogy with a discrete kind of variation, is that if you tabulate all the values of R in the horizontal direction, and if you tabulate all the values of phi between 0 and 2 pi in the vertical direction, you will get a matrix. You will get a grid where each cell of that grid will represent a particular point on the surface. So taking all those points means that for any particular value of phi, all the values of R are taken, and for any value of R, all the values of phi have been covered. So this is how you put the limits, and you find the 2 integrals separately, because the limits don't depend on each other. The limits are totally independent of each other. The limits of R do not depend on phi, and the limits of phi do not depend on R. So I get this integral, which is the answer for the conical part. Now the spherical part is again V. So now the dA vector for the spherical part points in the r cap direction. So taking the dot product gives filters out only the r cap component of V, and I get this integral. And to cover the entire spherical surface, you can think of this on your own, that R is already fixed, but if I vary theta from 0 to pi by 6, and if I vary phi from 0 to 2 pi, I cover all the points on the surface, and I get this integral. And then I just do an algebraic addition of the two, and I get this. And you can already see that the 2 integrals are equal. So the divergence theorem works, and it works very well. The answers are exactly the same. So we calculated a particular integral, which is the integral of the divergence of a vector field. That it could have been any vector field. We were given just one vector field. You can check it out for any other vector field that you desire. You can write down any vector, any simple or complicated vector field. What is a vector field? A function of r theta and phi, which is a vector. So a vector which varies, which has 3 components, and the components will be along r cap, theta cap, and phi cap, because we are using the spherical coordinates. The vector will have these 3 components, and all the 3 components will be functions of r, theta, and phi. Not all of them have to be functions of all 3 of them at the same time, but in general they would be. So the most general example would be like each of the 3 components would be functions of r, theta, and phi. So you can take any complicated function or any simple function that you desire, and you can do this again on your own. because you know that the elemental volumes and elemental areas, you know the method, how to think about them. And you can also try it with some other surface. For example, you can try it with a simple surface like a sphere centered at the origin. So it's a closed surface. You can try it with that. Or you can use the same volume, you can use the same vector field and use a different surface. Instead of the ice cream cone, you can use a sphere which is centered at the origin, which has a particular radius r. So it will have a volume which you'll use in the first integral on the left hand side integral. So you'll take the divergence of V and you'll multiply it with the volume, elemental volume, and then the limits would be different. You know, the difference that would come would be in the limits. That you would have to define different kinds of limits to cover the entire volume inside the sphere. And for the right hand side, you would integrate over the entire spherical surface. Only the surface. So we learned a lot of things in a lot of detail in these two videos, and it would really pay to sort of watch these videos 2 or 3 times and kind of go along with a notebook, writing down your own thoughts or writing down the equations as I talk about them, or drawing figures as I talk about them, and try to really have a feel, try to really have a close understanding of what is being talked about. That would make these videos really useful, which is what I intend them to be, you know, as tools for learning, rather than just videos that you can sit back and relax and watch. Then they would be of no use, because then you'd forget it a couple of days later. So I wanted to make a video which would trigger some kind of thought process or learning in you, and that would only happen if the viewer engages with the videos by working alongside, by writing something alongside, by thinking about it, by pausing the video at every point where he's confused. You know, wherever you're confused, you can pause the video and you can watch all over again, watch the last part again, or you can think about what I said and you can try to come up with your own reasons, try to come up with your own explanations, try to better the explanations which are given in the video, or try to point out any mistakes that were made in the video. That would really make it very useful. So thank you, thanks for watching, and bye.